This is Algebra 2 with Trig. This is Unit 6C review. So we're going to expand. So we're going to take the log base 7 of 5 plus log base 7 of x squared plus log base 7 of the square root of y. So because they're multiplying, we put pluses in between. So now really the only thing I can do is bring my power up to the front. So log base 7 of 5 plus 2 log base 7 of x plus, here we have y, the square root of y, which is the half power, which we would bring the half to the front. Here, when you have a subtraction, let's do it in different steps here. So a cubed, subtraction is going to be minus log base 2 of bc squared. Now we have multiplication. Then we have minus. Now when you have minus, you want to subtract this whole quantity. So you must have parentheses because you want to be sure it's distributed correctly. So log base 2 of b plus log base 2 of c squared. Then we'll need to distribute that in when we write our final answers. We can bring the power up to the front. We would have negative log base 2 of b minus, bring the power up to the front, here natural log is just the same thing, so I see a fraction, so I'm going to say natural log of 3. Now instead of writing the radical, I'm going to write it as f to the 4/5. That's writing it with fractional exponents. Minus the natural log of g squared. And then we can split this apart to the natural log of 3 plus the natural log of f to the 4/5 minus, we can bring the 2 up in front, the natural log of g. And we can bring that power to the front. So you take it to the front of its own logarithm. Now we're going to condense. So here, the first thing I'm going to think about doing is reversing our power property. So we're going to have log base 5 of 2 to the 3rd power plus log base 5 of x to the half power. Now this doesn't have parentheses, so this is minus log base 5 of y to the 7th power plus log base 5 of w. The only value that goes to the denominator would be the y to the 7th. So we have log base 5 of 8. Because it's a plus, we would have the square root of x, because it's multiplication. The exponent that's a half represents the square root. The minus is telling us that this is going to be in the denominator, but since this is a plus, it should be up top. Where you want to fit it, it could be next to the 8. That would be very convenient. It could be afterwards, however you like to write that. Using the power property, so this is log 64 over 8, because 2 to the third is 8, and that goes into there 8 times. Here, when we have two logarithms with a plus in between, we can condense this into one logarithm by multiplying our two binomials. So you could write this as log base 4 of x squared minus x minus 6. Bring over your power property. Now, because they're both minus, they're both going to go into the denominator. So we have log base 2 of 5 divided by d to the 6th power h to the 7th power. So here we're looking, the base is 3. I can't get this base, the 7, can't be broken down. So we need to say log base 7 over log base 3. We could use a calculator to do that. Log base 7, this is the change of base formula. So use the change of base formula, and that was approximately 1.77. Here we could say log base 3 over log base 8. So you could do it the same way. Log base 3, you've got to put parentheses around that, divided by log base 8. You can close the parentheses or not, doesn't matter. The other method you can use is alpha y equals. Go over to window, which is the functions, down to number 5, which is the logarithm. And you can put in the 8, and you can put in the 3, and you should get the same exact decimal. With our last one, we'll do the change of base formula, log of 14. The number on top, the larger of the numbers, not the value that's larger, but what you're taking the logarithm of goes on top, and the base value goes on bottom. And I've shown you two different ways to type it in the calculator. So log of 14 with parentheses divided by log of 5. That'll be just fine. So if we're rounding it to the nearest thousandth, we look at the 10,000th. That makes it a 10, which rounds it up to a 4. So 1.64. So here, if we can make the bases the same, that would be convenient for x plus 2. 8 can be made of 2 to the 3rd power, and that still has an x plus 2. Notice you cannot make 2 to the third power. You cannot make it look like an 8 because this isn't an 8. This is an 8, but it looks like a 2. There's a difference. 2 to the 4x plus 2, and you multiply your exponents, 3x plus 6. You've got to distribute that through. Now, since the bases are the same, we can set the exponents equal to each other. So x is going to be 4. You can plug that back in and see if it makes sense. It's always an option. Not sure you'll have a calculator for the test, but you'll definitely have a calculator for your homework. Get some crazy number like that. And you'll see that both results were the exact same. So here we can make this 9 to the negative 1 power. And then 9 can be written as 3 squared. That's 9 to the negative 1 power. And we would need to distribute. So we would have negative 2x plus 6 equals 3x plus 1. Be sure to distribute that through correctly. So 5 equals 5x. So x is going to equal 1. Here we don't have the same situation. We can't make both the sides of the equal sign the same base. But we can solve for an exponent by using a logarithm. Remember, a logarithm always equals the exponent. The base of the exponential is the base of the logarithm, and your 18 is what you're taking the logarithm of. So we're going to do log of 18 divided by log of 7. Gives us 1.485. And then to get the x by itself, we need to divide by 9. So 0.165. So x is approximately 0.165. And we can test that off if we want to. 7 to the, let's use the right number, 7 to the 9 times your answer. If you use the real answer, the previous answer, you can make these answers match up. And that equals 16, just like we have. We would divide by the leading coefficient. Now we're solving for an exponent, so we can use a logarithm. Whenever you have the e as a base, you're going to use natural log. Natural log of 12 equals the exponent. Logarithm always equals the exponent. The natural log of 12 is 2.485. and then we would add 3. If the logarithms are the same, you set your expressions equal to each other. X equals -4. Here we have a logarithm, not on both sides. We have a logarithm that equals an integer, so we're going to turn this into exponential form. 5 to the 3rd power equals 3x plus 2. We don't need the logarithm to solve for the exponent because we know what the exponent is, so no need for a logarithm. So this is 125. We'll subtract 2. We divide by 3. We get 41. Here, the 1 is not in parentheses with the x. It's not the natural log parentheses x plus 1. They're separate. So you can subtract that away. So 6 times the natural log of x equals 30. We can divide by 6. So we need to use the base. So 5 to, actually e to the 5th power equals x. There's e to the 5th power equals 148.413. We have 2 logarithms that are being added together, so we need to condense. I'll make that note here. So we're going to have log base 6. I like to put the monomial first and the binomial second. So we're going to write this as 6 to the 2nd power equals our x plus 9. Distribute gives us x squared plus 9x. We'll move our 36 over. So we factor that apart. We know that 12 times 3 multiplies to be 36. If we want them to add to be a positive 9, you got to have a positive 12. So we use the zero product property. Now we need to check our answers. We need to see that when we plug them back in, if we have extraneous solutions. So when we plug in a -12, that gives you a -3. That's extraneous. So we make an X on that and say extraneous solution. If we plug a 3 in here, we get 12, we get 3, no troubles with that. So that's our real answer. Let's go back and check the other ones just to be sure. So we haven't talked about that yet. You plug 5 in, you can't mess that up. -4, oh look, -4 gives you -12 plus 7 is -5. That's -5, but e to no power equals -5. So we can cross that off no solution. Missed that one the first time. 41 would have no problem, and the rest are fine. All right. So log, it's a common log, so the base is 10. 2x times x minus 5 equals 2. So a common log means the base is 10. So we have 10 to the second power equals 2x squared minus 10x. This becomes 100. We subtract the 100 over. Divide everything by 2. So we have 0 equals x squared minus 5x minus 50. So x looks like 5 and 10. It's got to be a negative 10 and a positive 5 if they're going to add together to be negative. So our zero product property would give us negative 5 and 10. And if we plug a negative 5 in, we would still get negative values. So that is an extraneous solution. But the 10 does not give us a 0 or a negative, so we're just fine. We have our story problem where we're going to deposit $800 that has an interest rate. About how long will it take for the balance to triple? That's a new one. So if we do quarterly, we're going to say A equals P 1 plus R over N to the NT. Quarterly means that N is going to equal 4. We want the deposit to be 800, that would be the P, and we want the balance, the total amount, to be triple that amount. So 3 times 800. We're going to start with 800. We move our decimal spot over 2, so we're 0.0225. When you are compounding quarterly, we're going to do it in quarters. And we want to know how long it'll take. So what are the years? What's the T? So this is 2400 equals 800. This is 1 plus 0.0225 divided by 4. Only the decimal is being divided by 4, not the 1. So we get 1.005 to be as exact as possible. We'll just keep all those values in there. We'll divide by 800. We get 300. Now we're solving for an exponent, so we need a logarithm. So using our calculator, we have log of 300 divided by log of 1.005625. And divide both sides by 4. That was the change of base formula we did with the calculator. So looks like 254.21. And some would say that we would need to round this to the nearest quarter. I'm not too concerned about that, but some are going to say that this would be 254. We didn't make the whole quarter. We didn't get all the way up to 0.25 because we're breaking it into quarters, doing this quarterly. So you could say it's approximately that much. Those are years. Not very realistic, but all right. Continuously. A equals PERT. So we want our amount we start with to triple. So we divide by 800. The 800s cross off. We don't even need to call it 2400. And we would say the natural log of 3 equals the exponent. The natural log of 3 gives us 1.098, and that would be 1.099. And we can divide that by 0.0225, 48.827. Those would be years. Find the inverse. We switch our x and the y. And then for us to get into our logarithm, we need to write this in exponential form. This isn't in inverse function notation, so I'm not going to write it with f of -1. So e to the x power equals y plus 1. E to the x minus 1 equals y. Switch our x and the y. So log base 7 of x equals the exponent. Logarithms always equal the exponent. We would add 2 to the other side. So x plus 2 equals the exponent. So that's 3 equals the exponent there. And we'd need to say the logarithm base 3 of x plus 2 equals y. If we were going to graph a logarithm, this is kind of a review, we would want to consider the equation y equals log base 3 of x. And we are going to convert that into exponential form. Pick our values for y, and when we put a y, a -1 in for the y, we get 1/3, 1, and 3. So So when x is 1/3, we're at -1. When it's 1, we're at 0. And when x is 3, we're up at 1. You could go farther. Plug a 2 in here, you get 9. So when x is 9, we're up at 2. Just to give you an idea where the graph is really heading. So notice that the graph goes down. It goes down forever, so you really want to be sure there's arrows on it. You want to draw in your asymptote. That's x equals 0. Typically we don't draw the asymptote till after we do our translation. Looks like I got carried away. We're going to go 2 to the right and 1 up. 2 to the right and 1 up. 2 to the right and 1 up. So that would be an asymptote at your h value. So the asymptote is x equals 2. The domain is every value greater than your h value. And your range is all real numbers. When we're approaching for the end behavior, we can only get close to 2. We can't get to 0. We can't get to negative infinity for sure. The y value at that point is heading down. As we move to the right, we can actually plug in any number to the right, and the graph slowly keeps increasing. So we have our graph of log base 3 of x, and we have our graph of log equals, or base 3 of x minus 2 plus 1. We're all set.